So far we have taken 3 classes on fractals, and this is the 4th one, in which we will mainly try to understand how to generate fractals by a method that is not the same as the Mandelbrot or Julia sets. And in order to do that, we had proceeded by the functional analysis approach, in which we had defined the space of all possible images, all possible compact subsets of the R2 space. We had shown that that space is complete. If we take steps, then all my steps will fall on the elements of the space, and then we proceeded on to defining how to take the steps. And we said that the simplest possible way of taking a step from a point to a point is by a affine transformation. Affine transformation given by x n plus 1 y n plus 1 is equal to a b c d x n y n plus e f. It is not difficult to see that these two fellows define translation, and these 4 fellows A, B, C, D, they define rotation, flipping and stuff like that. In order to visualize what these 4 people do, it is easier to represent it in terms of r theta coordinates, so that this can also be, this thing can also be written as r1 cos theta 1 minus r2 sin theta 2 r1 sin theta 1 and r2 cos theta 2. What are these angles? Well, it is not difficult to see. Suppose you have a 2D coordinate system in x, y, and you have defined a square 0 to 1, 0 to 1. Now, if you apply this transformation onto all the points of the square, what do you expect it will happen? What will happen? The square will be deformed in some way, and it is a linear transformation. And since it is a linear transformation, lines will still remain lines. So, you expect the square to become rhombus, that kind of stuff. And so, this, in order to facilitate drawing, let me draw it here. It will, you expect it to become something like this. Okay. Obviously, there would be 2 of those sides. They would have the sizes of r1 and r2. That is how you interpret the angle by your theta 1, and the other one I cannot represent here by the what is called. Anyway, we can visualize that. The point is that the ABCD matrix essentially does things with the thing rooted at the same point, the origin, and then these 2 fellows give the x coordinate shift as well as the y coordinate shift. So, that is how you can define the steps. Now, I also said in the last class that suppose you have some kind of a figure to start with, and you define one transformation, say it makes it like this, and you have another transformation, say this one is W1, you have got another affine transform that makes it, say, like this. Then you might say ultimately I have the W1, which is the union of these 2 sets. So, it will be this way we can add a little bit of interest to the things that we ultimately construct. So, if this is the product, the result of application of this transform on the original set, and this is the product of the application of this transform on the original set, then the ultimate thing is the union of this and that. Okay. So, that is the essential idea. How we actually apply it and what we derive out of it, get out of it, we will come to that a little later. But first, let us concentrate on the character of these transforms. We at least in the last class you have seen that we are homing onto something, that is, we will start from any image and we will define some kind of transform that will transform that image, but we will then apply the same idea that we did in case of maps. We will keep on applying it. Ultimately, if certain conditions are satisfied, then that will converge onto something. Something will be an image. That is the idea. So, in case of the maps, when we are talking about maps, we also had the fixed points and the convergence onto the fixed points, right. We are following the same kind of idea, but then we have to do something in order to ensure that they do converge. We should not really define some kind of a transformation that will keep on going, moving away, ultimately not converging onto anything. That is not what we want. We want convergence. And for convergence, the crucial concept is contractivity. The contractivity is simply as follows, that if you have one point x and another point y, and you know the distance between them d of x y, and then you define a function f of y and f of x, it lands here, it lands here. Here also you will have a distance d of f x f y. Am I writing in the sufficient size so that you can see? Yeah. Now, if this distance is smaller than this distance, then the transformation will be said to be contractive, common sense thing. Okay. So, it is contractive or it is said to be a contraction mapping if is less than equal to some s times d of for every x, y, a member of the set x. Okay. Now, this s is called the contractivity factor. Fine. Good. Okay. So, once we have defined the contractivity factor, by the way, if you have the mapping that we did earlier, this one, what will give the contractivity factor? What will ensure that it is contractive? The determinant should be less than 1. Simple stuff. So, if we simply ensure that the determinant is less than 1, we are through. The mapping is contractive. Now, if the mapping is contractive, that means we have defined something that is contractive, then quite a long time back some very interesting and important theorems were proved that apply to contractive mappings. Naturally, immediately those theorems will become applicable to what we are doing. One of the very important theorems, crucial theorems in functional analysis is called Banach's contraction mapping theorem. How many of you have done a course on functional analysis in maths department? None. Okay. In that case, I have to do this ab initio. That's fine, no problem. Only thing is that while we do this, you switch the mode of thinking to a mathematical mode of thinking. When we say x, then that x could be a point, that x could be a line, the x could be a figure, x could be a function depending on what we have defined. So, if we say let x comma d, let x comma d be a complete metric space, essentially will mean that I am not now taking into account what that particular thing is. We are generalizing concept. We are generalizing and saying that x is a space in which I have defined the distance between two elements. That is it. Complete metric space means all the points in this space are defined. So, the switch in the line of thinking is necessary in the sense that we engineers are often used to thinking in terms of concrete things, and mathematicians talking in terms of the generalized abstract concepts. So, we will, when we talk about this, we will presently talk about the abstract concepts. You will easily see that if you in your switching mode of the thought, if you keep thinking in terms of points, that yes, x are 2 points, x and y are 2 points, fine, no problem. In fact, I find it easy to understand all these things just by visualizing this x and y as 2 points, but keeping in the back of my mind that these are all general concepts, they will equally apply to a set of functions, a set of images, everything. Okay. So, the Banach's contraction mapping theorem says that if x comma d be a complete metric space. What is metric space? Where d is defined. What is complete? That all Cauchy sequences converge onto elements that are members of the set. And T applied on x to x is a contraction mapping. Okay. So, T applied on x also falls in the space x, that is why T x to x. That is, contraction mapping would mean that the distance between T x, T y will be less than equal to some number contractivity factor times, let us call it lambda, times d x y, okay, where lambda is between 0 and 1 for every x, y member of the set x. See, these notations you should get used to. This is the notation for every. This is a member of the set. So, okay. Now, the statement of this Banach contraction mapping theory is that if this is true, then T has a unit fixed point. if this is satisfied, then there is a fixed point, it is unique, and the serial application, iterated application of the function t will always lead to a convergence sequence, and that convergence sequence will converge onto a fixed point. So, this has actually 3 components of the statement. Repeated application of t defines a convergence sequence. The convergence sequence converges onto the particular fixed point x, and the fixed point is unique. See, fixed point is unique is a very strong statement, because you have already seen that there are maps in which the fixed points are not unique. So, these are all reasonably strong statements. Let us prove it. This is the only proof that we will do here. The other proofs we will refer to some book, because if we keep on doing the proofs, it will become a mathematics course, which I do not want. We will actually like to do things more than to do the proofs, but this one I will prove, because this is half a century old proof. Banach was a Polish mathematician, which I learned died in the German concentration camp. So, there are historical interest in his life also. So, let us start. Let us say we start from a point x naught, apply the transformation t to arrive at x1, apply the transformation t again to arrive at x2, and so on and so forth. So, we can write x1 is equal to t x naught. Okay. Now, x naught is arbitrary anywhere, x2 is t x1, right, x3 is similarly, and so on and so forth. Xn is t x n minus 1 is equal to t to the power n of x naught. Fine. So, this is how we have defined a sequence, and then the next step is to prove that the sequence is a Cauchy sequence, right. We have already learned the definition of a Cauchy sequence, done that in the last class. The distance between any two elements of that sequence m and n, there will always be a number such that the distance is less than that. So, that is how Cauchy sequence is defined. So, we will try to prove that way. So, we are interested in the distance between x m and x n, right. Because the mapping is contractive, this will definitely be less than equal to the distance between, not because of this property, but because of the triangle inequality. Remember triangle inequality? We can write that x m and x m plus 1 plus d x m plus 1 x m plus 2, so on and so forth. Finally, we will reach d x n minus 1 x n. Okay. So, in that sequence there are say 2 points m and say n, then we are saying that the distance between this is definitely less than this plus this plus this, right, and we are stating it that way. It is the triangle inequality. Now, this we can further write as this number in the right hand side, we can equate to d of t of what is this x m minus 1, right. T applied on x m minus 1 yields x m, comma t of x m plus d of same way t of x m plus 1 d t of x n minus 2 t x n minus 1. Is it going out of the screen? No. So, we have just taken one step back, right? We have just taken one step back. So, what is holy about it? Nothing. Only we can now write that now this should be less than equal to lambda times d of x m minus 1 x m plus lambda times d of x m plus 1 to lambda times d of x n minus 2 x n minus 1. You can write that way. This is because of the contractivity factor, lambda. Okay. Good. Now, notice I will come back to this one a little later. Let me write somewhere else. Now, notice that the distance between x m and x m minus 1, one step, is equal to the distance between t x m minus 1 t x m minus 2, okay, which is less than lambda times the distance between x m minus 1 and x m minus 2. So, this way we are just going one step back. All these are just application of this step into various phases. Similarly, in proceeding the same way, we can write d of x m minus 1. Already we have obtained this. We can write this is less than equal to this lambda square, another step back, x m minus 2 and x m minus 3. Okay. So, this is equal to, this is less than this. In the next step, we can go one step further back. So, we get this. Okay. It is not difficult to see that this way we can go further and further back, ultimately ending where? The first step, the distance between x naught and x 1, right. Now, let us come back to here with that logic. If you go by that logic, then all these terms can be related to the first distance between x naught and x 1 as. So, this will be equal to lambda to the power m, the distance between x naught to x 1, plus lambda to the power less than equal to, yes. Well, this term is equal to, but ultimately this is less than equal to. This term is equal to next step. Less than equal to is the right thing to write here. So, m plus 1 d x naught x 1 go on, you ultimately get lambda n plus 1 d of x naught x 1. So, you can now take it common, d of x naught x 1. What do you have left? It is going on increasing. M is one step and n is some step later. So, it is going through that and ending here. So, you have this is nothing but less than equal to d x naught x 1. We will take lambda to the power m common. We have 1 plus lambda square plus, what does it end? Lambda to the power n minus m minus 1. This term is not very important, because in the next step we will say this must be less than must be less than. If up to this point it is less than, then we can easily add up to infinity and say that it is still less than that. Well, now this one you can shorten it and write it as right, very important step. Now you see we have, let me write that again here, xm xn. The distance between two steps, two things, and we have related to this. Now you see, if these things go to infinity, what happens here? Lambda is a term that is less than 1. If m goes to infinity, then obviously this goes to 0. So the distances shorten progressively. Ultimately, that must become a Cauchy sequence, right? So this is nothing but a Cauchy sequence. So the point that has been made yet is that if you can define a contraction mapping T, repeated application of the contraction mapping will define a Cauchy sequence, which means that it should converge. Fine. Now, if it converges, the next step is to prove, suppose it converges onto the fixed point x star. We will use this particular sheet later, I will keep it here. Okay. There are two more elements we need to prove. One is that where it converges, suppose the sequence x0, x1, x2, so on and so forth ultimately converges to, and we need to prove that it is a fixed point. Fixed point means x star is equal to t x star. We need to prove that. Now that comes from distance between x star t x star must be less than equal to distance between x star and some element x n plus triangle inequality x n t x star. We are using the triangle inequality. So this is nothing but less than equal to d x star x n plus d of, we will just take one step back, t x n minus 1 t x star. Now we can again write this as d of x star x n plus d of, sorry, lambda will take out, d of x n minus 1 x star. Now as n tends to infinity, what happens to this one? By the earlier proof, this goes to 0 and this one also goes to 0, and therefore this thing goes to 0, and therefore the distance between x star and t x star must be 0. So that proves that it converges onto the fixed point. Lastly, we need to prove that the fixed point is unique, because ultimately what we are going to do, use these theorems ultimately to do things, and we need to make sure that we ultimately do converge onto the things that we want. It has to be unique. So proof of uniqueness. Proof of uniqueness, in this proof you start from the assumption that there are two fixed points. So fixed points are x star and x double star, say. Suppose there are two fixed points and will lead to a contradiction. Then d of x star to x double star, what is this distance? Equal to d of t x star, because it is a fixed point, x star is equal to t x star, and t x double star, this is also a fixed point. So, this must be then less than lambda d of x star x double star. Obviously, this is a contradiction because the number cannot be smaller than the same number. Obviously, this is a contradiction. So, this leads to the conclusion that x star must be same as x double star. They cannot be two different points. So, if you have a contraction mapping, it proves, the Banach contraction mapping theorem proves that if you repeatedly apply it, it will always converge. It will converge onto the fixed point, and the fixed point is unique. Okay. Now, how to apply that? Let us first try to do that on a one dimensional map. Suppose we start from the distance between 0 and 1. If I now say that x n plus 1 is equal to 1/3 of x n is my map, is my W1, what do you get out of this? In the next iteration, it gives a this much. All right. If you keep on applying it, it ultimately converges to a point, right? Now, let us define another W2 as x n plus 1 is equal to 1/3 x n plus this other contraction mapping. This is contractive, right? 1/3. So, these are both contraction mappings. Now, if I say ultimately my mapping is the union of the two, what have you? This and that put together will now be my capital W. So, capital W is this step, which is the union of W1 and W2. Repeat this procedure, what do you have? The Cantor set. Yes, we have already done that. So, if you repeat this procedure, it converges onto the Cantor set. Okay. So, here we have a contraction mapping defined, a contraction mapping in which both these are contractive. Ultimately, that converges onto a point. If you start from the Cantor set and apply this, it again converges, it again lands on the Cantor set. The Cantor set itself is the fixed point. Okay. Now, let us go forward. Now, suppose I have in the 2D space defined two of the W's, two of the contraction mappings, and putting them together, union of them is defining my ultimate mapping. What would be the resulting contractivity factor? You get my point? Here both of them had the same contractivity factor, 1/3, but we might have a situation where you have both of them having different contractivity factors. So, suppose I am working now on the 2D space. Okay, let's look at it from another angle. If a point maps to a point, another point maps to a point, and I have defined the contractivity factor between these two as S. So, T of x and sorry, x and y, T of x, T of y, this contractivity factor we have defined as S. Now, if this same map is applied to a set yielding another set, what will be the contractivity factor? Same. You get the point. So, if I have a B, C, D, E, F defined, that means A, B, C, D, X, Y plus E, F. This defines how a point maps to a point. This could be applied to a set yielding another set. The question then is, for the set, how much is the contractivity factor? Is the same. Okay. So, this is another theorem which I will not go into the detailed proof. You can intuitively understand it, that is why I am not going into the detailed proof. If you want the proof, you can simply, better I will refer you to the book where the detailed proofs are obtained. This is Michael Burnsley's Fractals Everywhere. It is a very good book from which the detailed proofs you can get. If you want to get into the proofs, it is fine. Okay. So, let us now suppose I have defined a W1, W2, W3, and ultimately I am saying that my W is W1 union W2 union W3, and W1 has a contractivity factor S1, W2 has a contractivity factor X2, and W3 has a contractivity factor S3. Then what is the contractivity factor of yes, again that follows from common sense, and therefore there is no point is going to a detailed proof, is the maximum. So, the contractivity factor of capital W is why? Proof kanu kya? See, I can go into the proofs, but all the proofs will get a little crumpy. You can see that ultimately you have one set, with the help of one of this you get a smaller one because it is contractive. With the help of the other one you get another one, with the help of the third one you get another one. The contractivity from here to here is given by how points, the distance between the points, right. It is not that how much that does the total set shrink, no, that is not the contractivity factor. The contractivity factor is given by the distance between points in that set, and that obviously will, in some cases it will have the contractivity given by S1, in some cases S by S2, but ultimately if I say what is the maximum contractivity, maximum contraction between points, that will be the maximum of all these. Well, a hand waving argument is like that, but if you want to have a detailed proof, just look at the proof. These are all given. Fine. So, if I choose a few maps with contractivity factor less than 1 and only make sure that all of them are less than 1. So, if we have chosen the individual transformations W1, W2, W3, W4 and all that, each we have to make sure that they have contractivity factor less than 1, and that is enough, because then ultimately what we have must have contractivity factor less than 1, and therefore it must contract, it must ultimately converge onto something. Now, let us go to this theorem. Let again x what is this? X are the is a set and Wn are the transformations defined with various transformations W1, W2, W3, W4 and all that. These are the transformations. This taken together will be called the iterated function system. Function system means these W's are the functions taken together, it is a function system, and you can iterate it. That means you can repeatedly apply this transformation. So, it is called a iterated function system. Remember this particular word IFS will appear repeatedly in our discussion. So, remember IFS, iterated function system. We generate all fractals using iterated function systems. That is why this is so very important. Now, notice look at the theorem. It says that if you have this an iterative function defined, the transformation W, capital W, defined by W of the set B is the union of Wn of B. Do you understand what is said? This is my set B. W1 yields this one, W2 yields this one, W3 yields this one. So, ultimately the union is the result. So, from B to capital W of B is the transformation. Okay. The transformation is not by the individual ones, but union of the individual transformation is the ultimate capital W what we are talking about. This is the iterated function system. Capital W is a function system. Go on iterating it. That means you apply once, you get this, you apply again, you get something else, you again you get something else. Ultimately, it will give a sequence of images, and that is what we are talking about. Now, this is the mapping, and suppose this is a contraction mapping. Which means the Hausdorff distance between, now I will write H because we have already defined the Hausdorff distance. Hausdorff distance between W of B and W of C should be less than equal to some S times H of okay. Then if you have, if this is a contraction mapping, then the Banach contraction mapping theorem would say that this has a unique fixed point and the iterated steps will lead to that. Okay, that will be written as ultimately the suppose the fixed point is A, is say A. So, A is equal to is nothing but union of what does it mean? Means that A is unique. For every such transformation we have defined, we can define A, the fixed point is unique. It is an image, and starting from any other image, say B, we can repeatedly apply this transformation and ultimately converge onto A. So, do you see the logic slowly emerging? For any given image, I will somehow define this W, and then starting from any given image, I can repeatedly apply that transformation and ultimately we will converge onto the final set. Mathematics says so. Now, it might get very counterintuitive though, because actually I wanted to show some of these things, but nevertheless we can do that. I will just flash some of the images here so that you can see. See, here we started from, can you see that? We started from a black triangle, and we have a set of W's given which give these three, each smaller, thereby these are all individually contraction mappings. Keep on applying that, ultimately it converges onto this Sierpinski triangle. It might be a different starting point. For example, you might start from a square, apply the same transformations, you ultimately get the same stuff. This is the attractor. Okay, can you see that properly? Yes. So, this is the attractor. For this attractor, somehow we need to define the set of affine transformations, and then I do not care what my initial condition is. Wherever I start, if I have these numbers, ultimately I will converge onto this. This is the confidence given by the Banach's contraction mapping theorem. Good. Now, let us proceed. How much time do we have? Probably about 3 minutes or so. Fine. Okay. Now, what I will do is, I will tell you how to do this. For example, for the Sierpinski triangle that you just saw, the A, B, C, D, E, F, you will need a few of them. You can easily see that you need 3 of them, right? So, you need, I am defining it as x n plus 1, y n plus 1, A, B, C, D, x n, y n plus E f, and you will need, this is say W1, you will need 3 of them. So, you will need 3 values of A, B, C, D, 3 values of E f. I will just put that in a table. W1, W2, W3, you will need 3 of them, A, B, C, D, E, F, 0.5, 0, 0, 0.5, 1, 1, 0.5, 0, 0, 0.5, 1, 50. 0.5, 0, 0, 0.5, 50, 50. How to generate these numbers, I will teach you, do not worry. But presently assume that God given. Somebody gave you, and now today's task is to to do what I just showed you, that means starting from any given image to ultimately converge onto that. How to do that? What we will do is first start from any possible image, say a square, say a circle, say a arbitrarily shaped triangle, whatever it is, which will be nothing but a set. There will be points in that set. There will be points in that set. So, suppose you have started with a square, there will be points in that set. And you might say that you are talking in terms of pixels, it will be easier for you to work in pixels. So, say this is 0 to 100 pixel, say. You might as well scale depending on the resolution of your screen. Then take the first one, W1, which means A has 0.5, B has 0, and so on and so forth. Apply this to all the points of this square. All the points means you immediately run into the question, how many points? As many as the number of pixels in the square. Okay, as many as the number of pixels. So, it will go somewhere. It will go somewhere. Now, take the next one, do the same process, it will go somewhere else. Take the third one, it will go somewhere else. Then you started with these pixels filled. After the first iterate of W, you end up with these pixels filled. In the third iterate, in the second iterate, you start with these pixels and apply the same procedure. It will ultimately converge onto something. You will see before your eyes how an image, as you apply the contraction mappings, change in shape and ultimately it converges onto something very interesting. In the last class, you have also seen the image of what did I show? Probably the fern I showed and the snowflake, right? Okay, let's talk about the fern. That's interesting. Write down the iterated function system of the fern, and you write the program to generate the fern. You have understood how to write the program now? Actually, the program is very simple. For the fern, again, you need 4 of them, W1, W2, 3, A, B, C, D, E, F. 0, 0, 0, 0.16, 0, 0, 0.85, 0.04, minus 0.04, 0.85, 0, 1.6, 0.2, minus 0.26. You might wonder who gave these numbers. Well, at the end of the day, you will be able to generate these numbers. You will be able to generate these numbers. 0.23, 0.22, 0, 1.6, minus 0.15, 0.28, 0.26, 0.24, 0, 0.44. Given these numbers, you will also be able to generate the fund. Okay. So, you have understood how to write the program to generate the fund. If there are any questions, ask. But try to do this before you come to the next class. This will not take more than an hour, I can tell you, programming. Fine? Okay. So, that is end of the today's class.